Gonna present our work on runtime analysis of world system provenance. So part of the work was done when I was a PhD student at the University of Cambridge and while I was a fellow at Harvard University. So let's get started by talking a bit about provenance. So you probably heard about provenance in the field of science, where they're trying to look at reproducing scientific experiment by understanding the origin on a figure and by tracking the computation that has been done on that figure down to the original data set. And the first application of provenance to security looked at similar ID. So the ID was when an intrusion is detected, to track back this chain of events to understand what happened. So for example, if you were in the forensic section, there were some people there working on using provenance to understand intrusion in the cloud, if I remember correctly. And that date back to first paper in 2003 in SOSP. And more recent work has started to look at provenance to do access control. So understanding the origin of data to make access decision, implementing loss prevention scheme. So deciding if a data has dependency to an event, not to an event, to some item of data that is confidential or secret, to not allow that data to leave the system, or even more recently to look at intrusion detection. So for example, our own work last year, or perform more in the DARPA transparent computing program that look at using provenance to do intrusion detection. So analyzes provenance graph to do intrusion detection. And so the thing is, we're moving towards complex runtime graph analysis. So it started from simple dependency, and now we are trying to do more complex graph analysis at runtime. And the problem is that the design of provenance system didn't change much from the time where we were doing scientific reproducibility. The capture mechanism has evolved, but the entire stack has not, as we're gonna see in the next few slides. And in the papers that describe the loss prevention scheme at Usenix Security, they describe the overhead, which is 21 milliseconds per packet, and this overhead grow over time with the size of the graph. The larger the graph, the larger the overhead. So at some point, the graph is too large to perform that. And a lot of work has been spent on trying to compress the graph. So either, as we've seen this morning, trying to compress pattern with templates, so things that are repeating, you can replace them by one node that represents a template in the graph, or by only capturing certain security relevant information. So for example, to combining with SE Linux label and only recording the provenance graph or security relevant process, etc. And what we try to do is to move away from that and allow to do runtime analysis by trying to rethink the way the provenance stack is designed. So previous work were post-hoc, so forensic kind of work, or had relatively high overheads that were dependent on the total size of the graph. And the prime was a legacy architecture. So what we want is a runtime analysis with a light overhead, which is independent from the total size of the graph, and that has limited memory usage, because the idea is not to put the entire graph in memory either. That won't work. And so we need to rethink the way provenance system of design, so the architecture of the provenance stack, the programming framework to implement that type of analysis, and the guarantee the system provides and the data model it uses. So now we're gonna have a very brief background. So we talk about provenance graph, but really when you start to look a bit on some of the work on provenance-based security at the operating system, we could as well talk about information flow graph. And what the graph represents is exchange of information between states of object in the operating system. So in this very simple example, you have two processes, P and Q, exchanging information over two sockets, S and T, and they send a packet A and Q send back a packet B. And we see the flow of information, and the version are created when information is incoming from another object and change the state of the object that receives the information. So it's a very small graph, but we have to imagine real system execution will have a million of vertices like that. And so the way that information is captured has been introduced in 2012 by the IFI system, by the team run by Kevin Butler, which was in the panel yesterday. And the idea is to use the OS reference monitor concept to capture exchange of information between control data type in the kernel, so kernel object, inode, superblock, socket buffer, etc., and to provide some completeness guarantee. So no details there, but in the paper we also describe how we can provide some extra guarantees. So let's now talk about what we did to overcome the limitation the previous system have to perform runtime analysis. So as I say, we needed to do change to the provenance architecture, identified appropriate programming framework to do graph analysis, and provide guarantee about the graph structure and ordering of event for the processing. So here we can see the stack of CamFlow. So that's the system we developed at Cambridge and Harvard. And that stack is not specific. Most systems adopt the same model. So SPADE, IFI, LPM, or the system developed as part of the DAPA transparent computing. And the whole idea is you have a capture system that record event, so exchange of information between kernel objects. That information is transferred to the collection layer that transforms those events into graph. This graph is then pushed into a database, and the application will query the database and do some analysis on the query. So that can be as simple as, is there a dependency on some confidential information, yes or no? That would be the case for example, the loss prevention scheme. And this whole architecture comes from the time where people were using provenance to do scientific reproducibility, this sort of things. And the stack has not been re-explored since with change in the type of application we're trying to build. So the idea we have is quite simple, is could we just implement analysis over the stream of provenance graph, over the graph, rather than having to put it through the database. And the idea is also to be able to deploy that type of analysis at different layer of that stack. So either directly at the same layer as the capture method, so as part of the reference monitor, sorry. So we can, for example, if we're trying to do provenance-based access control, so we can prevent action from occurring at the same layer at the collection mechanism to do user space analysis or on remote machine. So some of the change we made to the architecture is for the capture mechanism to directly produce a graph element. So most systems before logged system events that were transformed into graph. That was relatively computationally expensive on top of not allowing to do the analysis directly in the kernel because you need to restore event ordering without being able to rely on kernel data structures that are available when you're in the kernel, and not being able to reason about the concurrency in the kernel because you're just seeing what happened from user space and very sparse log of event. So that has been an issue in a number of systems. We decouple storage from processing because we still want to be able to do forensic application because that's useful, but we want to be able to do a more lightweight analysis as the system run. As I say, we allow the processing at different layer, and we provide a uniform framework to do so. So we want to write the application the same way, either if you're in the kernel or if you're in user space. So as a consequence, it has been implemented in C, so it can run in both space. We also looked at Rust, but didn't end up doing the implementation. It's also memory bound is not the right word, but there is a limit on the memory we use. We do garbage collection, etc., to only keep in memory the graph structure that is relevant for the analysis, and we're going to see a bit more detail about that in the next few slides. So we take inspiration from current graph analysis frameworks, so things about GraphSheet, GraphX, and the whole idea is that we can implement most of the provenance-based security as forward value propagation. So you propagate value along the graph. So the simple example you can think of is taint tracking. You can obviously do more complex computation, or you perform a directed graph traversal and you build a data structure that represents the state of your system. So you will do this kind of stuff if you're doing intrusion detection. You may build histogram or stuff like that representing the state of your system. And we look at a bunch of applications that has been proposed in the provenance-based security stuff, and we verified that we could re-implement equivalent application using our framework. So we look at loss prevention, we look at intrusion detection, provenance signature, information flow control, etc., provenance-based access control, and we verify the framework could re-implement that type of policy. And PowerPoint destroys resolution of my image, but basically the framework goes through the incoming edge associated to a node and the outgoing edge associated to a node, and you write the type of operation. That's very familiar if you ever use GraphSheet or this kind of framework. So in order to be able to do that and to have decent performance and not have to have the whole graph in memory, you need to provide some guarantee about the structure of the graph. So first, the graph need to be directed and acyclic. In the first place, provenance is supposed to represent causality relationship between state of object. So it seems reasonable to not have dependency in the future. However, a lot of systems to save storage space actually create cycle, and then you do some graph analysis to disambiguate the order of events. So you basically run an algorithm to remove the cycle, which is fine if your constraint is storage space, but if your constraint is runtime analysis, so you want to be able to process as fast as your system is generating provenance, that's not going to work very well. And actually, most whole system provenance don't guarantee the acyclicity. And on top of that, in order to do the processing properly at runtime, you need to provide other guarantees in which the event the graph element become available to the processing system. There is no need for total ordering. What is needed is ordering along paths in the graph. So the element along a path need to be published in the same order they occur. And all the in edge need to be published before the out edge. So if you think you're doing value propagation, you need all the value to have propagated to a node before you can propagate to the next node on the flow. And the next slide we show an example where it will be a bit clearer. And in the paper, again, we show some static analysis we do on our code and on the kernel code to demonstrate that it works. So here, if we look at the idea of why the ordering is important, what we want to guarantee is when we do the processing, we only need to recompute at most 2 nodes. So here, in our case, we will introduce edges 1 and edges 2 in the graph and F in that order. So when we insert edge 1 in the graph, we only need to recompute the value of B and E. When we inject edge 2 and the node F in the graph, we only need to recompute E and F as it is indeed recomputed. However, if we don't guarantee those order property, as some system does, what happened, for example, in the case of the edge 3, if we introduce edge 3 in the graph, we need to recompute D and C and E. And same case with edge 4, we need to recompute D, C, and E. And if you can place a graph element arbitrarily in the graph, you may need to recompute the entirety of your graph. And if you're trying to do runtime analysis, that will have adverse effect on your performance because you need to be able to query the graph. So you need a database to store it, et cetera, et cetera. So you can't guarantee good performance. So let's move to the evaluation. So we have 4 workloads for our evaluation. The vanilla workload, which is unmodified Linux kernel. The capture workload, which is simply capturing provenance. The nil workload, so that's a query that simply returns. So that's to measure the overhead of the framework. A loss prevention scheme workload that try to detect dependency to confidential data. The sign workload that's signing the provenance graph, and LPM, which is another capture mechanism as a sanity check, so we can compare our overhead compared to other provenance capture mechanism. So here is the result in a graph of the LM bench. So we can see that analysis, depending on this complexity, doesn't add much overhead compared to the capture. Our capture mechanism overhead is similar to that of other capture mechanisms, so LPM in this case we compare to. And if we look, for example, at the right and the sign query, what happened here is you can think of the query as being dependent on the complexity of the subgraph generated by a particular system call, and that overhead is independent of the cost of the system call itself. So if you have a very expensive system call comparatively to others, so for example, fork, this overhead will be the same in absolute value as for the right system call. But because the right system call value relatively is smaller, the overhead in percent or multiplier is much larger. And the sign query has a much larger complexity when compared to the nil and LPS query. So we run a macro benchmark similar to that presented in the provenance literature. So on the capture front, we have similar other overhead as other system. The framework itself add minimal overhead. The query obviously add more overhead, which is function again of the query complexity. And what we see here also is that postmark is really heavy on system call, and the most time you spend doing system call versus doing computation on your program, the higher the overhead will be for macro benchmark. So we see, for example, for the signature, it's 78% overhead compared to the vanilla execution. We also looked at query stacking. So we stacked 200 times the same query, and we looked at all the overhead. All the overhead varied. So it's a linear increase, which is what we expected, and obviously the postmark overhead is higher. We also look at the overhead in user space in terms of memory and CPU consumption. So we have two queries. Again, the nil query to see the overhead of the framework itself, and intrusion detection system query. So here the idea is to build a feature vector that will be later fed to a replicator neural network to detect outlier. So on the left, we have the memory usage. On the right, the CPU usage. As we see, the memory usage plateau at some point as we garbage collect the edge. And what we keep in memory is basically, you can think of it as the current state of the system, the object representing the current state, and we garbage collect older state. The CPU consumption, so what you see at the top is the IDS query, at the bottom is the nil query. You can see kind of two curves in each graph. So the top curve is the curve doing the computation, so that include reordering edges and from all we read them from the kernel, and doing the query and doing the garbage collection. And what you see at the bottom is a thread reading graph element from the capture mechanism. And it's maybe a bit small on the screen, but you can see at the beginning there is a spike. It's a provenance that has been buffered during boot time until the file system and the daemon that performs the analysis become available. So when you boot, you have a buffer to empty with graph elements that create a spike. Then it goes to some level, and then the normal processing starts. Takeaway. So runtime of analysis of provenance information graph is possible. We have a paper on the work that shows that we can do intrusion detection at the speed we generate provenance. The change required to the system are conceptually simple. Graph structure really matter, especially acyclicity and ordering guarantees. And some of the change we made probably affect adversely storage size constraint, and that will need to be looked in a comparison with that. And everything is open source as this address.
That's